Okay, so I figured out what's going on, and I got a little confused. So I had to start the video over because, well, started a new video. So this is part 2 of this lecture. So here we have A.high and B.low, but B.low is functionally equivalent, really equivalent to B bar. So then I can have A or B bar coming into this gate, and it's dot low because of the inverted output. Okay, now we have another inverted output after the inverter, so we have A or B dot low barred. Right, so that inversion is adding a bar over the whole thing. Now, this is a little bit more work than it's worth to me for this dot low, because I have a dot low and I have a bar, and we know those two cancel out. But let's get to that in a minute. So, down here we have A dot high and B dot low, so we have A and B bar dot low because of the inverting output. Both of those go into U4. Now this one gets a little bit tricky, and I don't like it. So this is where they take this dot low and added an extra bar. So that's where this extra bar over the top of this comes from. Similarly, this dot low becomes a bar over it. They add a dot low at the end because they need a F dot low in order for this signal to work. So what you can see is this A and this double bar over the A and B is going to cancel out. Right? So here's the equation that you get at the end of that wire. So the process is label the wires heading towards the end. So this one, that one. Before I label this, I need this one, and then I can combine them together, the output, get the equation, and then start to simplify. Now, the first thing that you do is obviously get rid of the double bar so that you just end up with A or B bar and A or B bar. Now, this needs that. Through De Morgan's, right, we can change this to A, B bar, A or B. Right, that's just De Morgan's again. Other video covers that more in depth. And that's what we see here. Now they're pointing out the fact that this is equivalent to A, B, or not A, not B. Another way to look at that, this is what, probably an XOR gate. You could prove that with a truth table. And then you're done. So that was analyzing that circuit. So we can look at another example here. I'll do this one a little bit quicker, hopefully less painfully so, because I don't like these dot lows. I would just stick with bars straight from the beginning. It won't go wrong. This book, too, is really focused on incompatibilities. My opinion is that it spends more effort worrying about that than is reality, because as a designer, people care about what your inputs are and your outputs, nothing more. They're not going to review your internal circuits, they're going to review whether your circuit works or not. So you need to be aware of whether you're active high or active low, because that's going to matter to the inputs and outputs, but worrying about the symbols in the middle of it is not worth your time, and the dot low adds confusion. If you like the dot low terminology, by all means keep it because it's what's in the book. Just be aware it is unnecessary. It's an unnecessary evil. That's a joke. But anyways, so what you're going to see, they're going to come down here. They don't need to label this net because it is what it is. They do need to label this net. I would say B bar, not B dot low. They say C dot low. I would need a bar. Then you can look at each of these the outputs of these intermediary gates. So U3, right, is just A and B bar. And it's barred because of this bubble. They say dot low. Repeat the process for each of those gates. Once you have those labeled, jump onto this gate and start adding the terms together that are added in, well, ORing the gates together, rather. I said add because of the plus sign. And you're going to throw a bar over the whole thing. Now, the thing to be aware of is CD is high, so CD is the same. A B bar is low, so it gets an extra bar over it, and C or D is dot low, so it gets an extra bar over it. And the whole thing gets a bar over it because it's inverting output. Okay. Onwards. This table is going to be very useful for you because it shows functional equivalencies, right? And here are big favorite ones, the NOR and NAND. I'm not going to worry. So this Fletcher's method, I recommend reading about it. You might need it for the homework. I'm not going to cover it in this because it's pretty straightforward once you do it. But again, it worries with this incompatibilities. I'm not going to put that on an exam. It's just on the homework. This is a nice example for it. It's walked through pretty well on this one, so I'll let you worry about that on your own. Because I need to get to the implementation of logic devices. I'm actually going to switch over to part 3 on this one. So.